Now continue from the previous slide. When we talk about fiber orientation, they are classified as either the continuous fibers. The fibers are classified as either the continuous fibers or discontinuous fiber. So continuous fiber are the long fibers and discontinuous are the short fibers. When the fibers are aligned, they provide the maximum strength but only along the direction. So in this case, they are aligned together. The direction is only, strength is only in the y-axis, and here the strength is only in the y-axis. But the composite is very weak in the other, but we don't want composites to be strong in one direction, because in terms of aeroplane, like says we got aeroplane wing, we want a strength in only this one direction. We don't want it strength in the all direction. We can figure out which direction the load will be applied, and if we know the direction of the applied load, we can only make the composite strong in that direction. Why? Because the major advantage of composite is the weight reduction. Fibers are quite heavy. We can add the fibers only in one direction, and then we will get the strength in that specific direction. In that one where there are short discontinuous fibers, the strength is uniform all across. So this type of fibers are used, composite are used where we need strength in all direction. Okay, so there is a term, we call it isotropic and anisotropic. Anisotropic is where we got strength in a very specific direction. Now let's have a look at the matrix material. We know the principal strength and the stiffness of the composite is provided by the fibers. The matrix material also have a large part to play along for the overall mechanical properties. Matrix cannot withstand high load as compared to fibers. Fibers are, the matrix distributes the load, fiber carries the load. Matrix binds the fiber together. It provides the ductility and protects the fiber from the elements, surface damages, corrosion, and other things. It separates the fiber and prevents propagation of the crack. So matrix prevents the propagation of the crack. Okay. It also prevents the fiber buckling under compression for certain type of matrix loading. Now, we need to make sure we choose a good matrix material that it can infiltrate between the fibers and form a strong bonding, interfacial bond. If the bond is not strong, we haven't made a good composite material. Now, we need to make sure the chemical of the matrix do not combine with the chemical composition of the fiber. Otherwise, they will combine and so they will make something else. And then they will cause damage to the whole composite. They will cause damage to the fiber. Hence, the composite properties will be very much different. There are three main types of composite material: PMC, CMC, MMC. Polymer matrix composite, ceramic matrix composites, and metal matrix composite. Now, the most advanced are the polymer matrix composites. Still under investigation. A lot of research are being carried out as we speak on polymer matrix composition, composites. Very high value, very niche design, blue chip companies, they only use that one. So not many applications so far because of the cost implication. So now for the polymer matrix, they are produced in large quantities due to their good room temperature properties, ease of manufacture, and they are low cost. Polymer can be thermoplastics or thermosetting plastics. There are advanced polymer matrix composite which are quite expensive as well. So these are generic ones. Then we got the ceramic. Ceramic are the main advantage is they are resilient to oxidation and deterioration at high temperature. They can withstand high temperature. They have a high melting point. They have a high compressive strength. example is concrete. Now, the issue with ceramic is whenever they will fracture, they will go through a brittle failure. They do not have a high value of fracture toughness. Now, to make them strong, one of the thing we can do is to reinforce with a fiber, whiskers, and plastics. Fiber, whiskers, and particles. Crack propagation is hindered by the presence of reinforced face. This is why in a concrete column or a beam, we have a fiber material, which are steel bars. And these steel bars are reinforcement, fiber material. We do not put aluminium. The reason is aluminium has a different coefficient of expansion and contraction. So in summer, you will see the concrete expand, but the aluminium rods expand more than that. So they will protrude out. And in winter, the concrete will contract and the aluminium rods, they will protrude in. So there will not be they will lose the bonding in 12 months when they see the whole season. And then there is no point. And then they will cause more damage. The coefficient of expansion, linear coefficient of expansion for concrete is 1.2 micrometer per meter, which is very much similar to the steel. They have the same coefficient of expansion, whereas aluminium has a coefficient which is around, I think, 3 times more than the coefficient of the expansion of steel or concrete. Now, the CMCs provide high temperature creep behavior and resistance to thermal shock. So this is one of the good advantages. Then we got the metal matrix composites. Now, the metal matrix composites, the matrix is the metal and the particles are something else. Okay, the use of metal matrix composite offers the potential of producing a composite with a high stiffness, high strength, and high temperature resistivity. It's a lot better than the polymer, but also better than the pure metal itself. They have better abrasion resistance, they have better creep resistance, they have better resistance of degradation by fluid like erosion. They have more dimensional stability at high temperature. They have non-flammability, they don't catch fire easily, but they are heavy, but they are expensive. Now, the matrix component in the MMCs are either titanium, either magnesium, either copper, or aluminium. The reinforcement materials are silicon carbide or alumina. In metal matrix composite, the fiber can either be continuous or discontinuous. Now, in MMC, the discontinuous fibers are more easy to use as compared to continuous fiber. The discontinuous fibers, as we said earlier, can be a shot, whisker, particles, or platelets. We use a technique called powder metallurgy to use this to create that one, metal matrix composite, or vapor deposition, or diffusion bonding, or infiltration of a liquid metal into fiber bundle under pressure. Powder metallurgy is a technique where we grind, convert that into tiny powder, and we apply the pressure and the heat, and it's bonded together. Things made up of powder metallurgies are usually expensive, but they have a very good wear and tear resistance. Vapor depositions is a process where the particulate converts into vapor and they are deposited on a atom by atom on a material. We can predict the mechanical properties of the material if we know the fiber properties and the matrix properties. Okay, now There are two geometries that we can examine. One is called isostrain and one is called isostress. Isostrain, iso means same, strain means change in length. Stress applied parallel to a lined continuous fiber in a matrix. Isostress is stress applied perpendicular to a lined continuous fiber in a matrix. So these are the two conditions, isostrain and isostress. Let's have a look at the isostrain. These are the fibers and you're applying a tensile strength. Now the component is loaded in parallel to the plane of the continuous fiber. Now in this case, both the fibers and both the matrix, they are under the strain condition. They are under the same amount of strain, hence isostrain, single strain. Even though they may have a different modulus of elasticity, different E values, but they are under the same condition. Now isostress. In isostress conditions, the composite is loaded perpendicular to the direction of the continuous fiber. In this situation, the stress on both the fiber and the matrix is same, single stress. The matrix will usually exhibit large strain due to its lower modulus. Matrix always have a lower modulus as compared to the fiber material. This type of loading condition will cause quick failure as compared to the isostrain condition. The materials are stronger in isostrain as composite materials as compared to isostress. Now, when a material's fracture, how the cracking happens in composite, when a material fracture, it absorbs the energy. The main form of absorption energy is in the form of the work. The amount of the work done on the material before it cracks represents the toughness. If a material can absorb a lot of energy before it fails, it's more tough. So there is more energy absorbed in a tougher material before it fails. Now, composites, they are unique factors that contribute to the energy absorption and result in tougher material. Now, the matrix is usually not a very stronger phase. Fiber is a load bearing, which can carry the load carrying material in a composite. But when the delamination happens, debonding happens, the material, the fiber is going to fail. When a crack propagates through the material, debonding occurs between the fiber and the matrix. Now, when this thing happens, after you apply a significant amount of the energy will absorb due to the fiber pull out. Fiber will just pull out because that's delamination. Work is required to pull the fiber out of their hole in the matrix. The amount of the work is dependent on the level of friction between, or the level of bonding between the fiber and the matrix. So this shows how the energy is being absorbed. So first the debonding happens, then the fiber is going to pull out. So there are two. One is a work done to cause the delamination, then the other is a work done to extract the fiber out. The material has already failed when the debonding happened. Composites are chosen because of the improved strength, stiffness, specific stiffness per unit weight. It's because of the lightweight. In aeroplanes, it's used to reduce fuel, increase acceleration, and the range of transportation. They don't rust. Good for marine and chemical environment. The need for maintenance and painting is reduced. Combine the excellent fatigue resistance, and composite can increase the product lifespan. The only issue is the labor. They are bespoke. The issue with the composite is end of life. When they reach their end of life, what are you going to do with composites? Difficult to recycle. Recycling pathway is almost non-existent in composite industry. Now here you go, that's the example. You can see composite in aerospace. All wing all that one is composites. So you can actually see